we want to talk about mainly two theorems. So the first theorem we are going to talk about is the Maclaurin's theorem. So the Maclaurin's theorem, here we are just going to expand functions in the Maclaurin's theorem. Then we are either going to use it to evaluate integrals or to solve a given value of that function. Are you seeing that? Then in power series again, we are going to deal with the Taylor's theorem. So in the Taylor's theorem, we are going to see how to get the Taylor series. And we are going to use that given Taylor series either to evaluate a given integral or to solve the value of that given function. Isn't it? So these are the two main theorems we are going to deal with in the power series. Are we together? So first of all, we shall start by defining a power series. Now any series where the variable is in terms of powers is just called a power series. Are we together? Any series where the variables is in terms of powers is a power series, meaning even a binomial series is a power series, isn't it? If you have a binomial series like 1 plus x raised to power n. So this is 1 plus nx plus 2 factorial over n into n minus 1x squared plus 3 factorial n to n minus 1, n minus 2x cubed in that order. That is a binomial series. You can see the variable is x, is in terms of powers. Are you seeing that? So it is a power series. So we want to see the power series which is going to give us the Maclaurin series and the Taylor series, our main interest in this topic. Are you seeing that? So you start by saying the polynomial function is the power series. Just start by saying a polynomial function is the power series. I want to explain what that means. The polynomial function is the power series. Start by saying a polynomial function is the power series. So you have to know what is a polynomial function, isn't it? Remember, when we are talking about a polynomial, we said an algebraic expression with exponents, variables, and coefficients is a polynomial, isn't it? So it means when you have an algebraic expression like this, a naught x naught plus a1 x1 plus a2 x2 plus a3 x3 plus until infinity. Here we are at a point whereby we are still defining the power series. Now if you have this, you can see the coefficients are the known component of the variable. The variable is the x unknown, the powers are the exponents. The powers are sometimes referred to as exponents or indices, isn't it? Are you seeing that? So these are the exponent, the variable, the coefficient. Meaning, if you have 2x squared plus 3x, you can see 2 is the coefficient, x is the variable, then 2 again is the power, isn't it? So here again 3 is the coefficient, x is the variable, then 1 is the power, isn't it? So if you add it was maybe plus 3, you can see here is x is raised to power 0. That is why it is silent, isn't it? So 3 is the coefficient, x is the variable, 0 is the exponent. So anytime you have an algebraic expression with the variables, coefficients, and exponents, then that is a polynomial, isn't it? So it means this is the standard form of a polynomial expression. Remember, it is an equation when you equate it to 0, isn't it? Are you seeing? But now it is a function when, because you can see, when you go to calculus, if you have y is equals to 2x plus 3, you see y is expressed in terms of x. So we say y is a function of x, isn't it? Because y is expressed in terms of x. So here we say y is a function of x. So instead of saying y is 2x plus 3, you just say f of x is 2x plus 3, because this f of x is the y. Are you seeing? So it means when you look at this polynomial expression, it is the variable here is x, meaning this polynomial expression, this algebraic expression is a function of x, isn't it? Are you seeing that? So that the function of x is what is equal to that. So if this is now a function, it is no longer an expression, it is now a function, isn't it? And which function is this? It is a polynomial function. Are you seeing that? Are we together? Yes. So that is why we are saying this polynomial function is the power series. Are you getting the argument? So the polynomial function is the power series. So when we start with the power series, before we go to the two theorems of the Maclaurin'S and the Taylor's, we found that the function f of x is equals to a naught x naught plus a1 x1 plus a2 x2 plus a3 x3 plus until infinity. This is where you reach, isn't it? Are you seeing that? So this is a polynomial function, and you've seen how the polynomial function is coming about, isn't it? Are we together? Yes. Now, we want to use this polynomial function to get the Maclaurin's series, which is from the Maclaurin's theorem, isn't it? So for you to get the Maclaurin's series, the first thing we want to do, we want to differentiate this function. When you are differentiating this function, you are differentiating a polynomial, isn't it? Are you seeing that? Yes. You are differentiating a polynomial. So when you differentiate a polynomial, what do we have? When you differentiate that, you get f prime of x. If the derivative is denoted as f prime, that is ordinary, isn't it? When it is partial, it is when it is denoted as subscript, isn't it? So if I differentiate f of x, it becomes f prime of x, isn't it? Yes. Are we together? Yes. And how do you differentiate a polynomial? So it is the power times the coefficient, isn't it? Yes. It is 0 times a naught, 0 times everything. See, the whole of this goes to 0. Yes. Then you go here, 1 times a1, it is a1, then you reduce the power by 1, isn't it? Yes. So if you have x minus 1, see, you have x raised to power 0. Yes. See, anything raised to power 0 is 1. Yes. So it means here you only remain with a1 when you differentiate x, isn't it? Then you move here, if you differentiate this, plus 2 times a2, it is 2a2. Are we together? Then you reduce the power of x by 1, isn't it? Yeah. You get x. Are we together? Yes. Then plus, if you differentiate this, 3 times a3, 3a3, then you reduce the power by 1, x squared. So maybe if I add another time here, a to power 4, x raised to power 4 like that, 4 times a4, then you reduce the power of x by 1. Like that, isn't it? So it means when I differentiate this f prime of x for the second time, it becomes f. When I differentiate for the second time, it becomes f double prime of x, isn't it? Are you seeing that? So f double prime of x you differentiate. When you differentiate a constant, you get 0. Remember, x raised to power 0 is what? Is 1, meaning this x raised to power 0 is silent, in other words. That's why when we are differentiating a constant, we are getting 0. That's why it is not here, isn't it? Are we together? Okay? So if you differentiate a constant, you get 0. And if you differentiate this one, 2a2 is a constant. If you differentiate x, you get 1. So you remain with 2a2, isn't it? Then here, 3a3 is a constant, isn't it? If you differentiate x squared, so you get 2x. Are we together? Isn't it? So 2x times 3a3, so you get 6a3x. It is just like saying 2 times 3a3, you get 6a3, then you reduce the power by 1, isn't it? Then you move to the next one, 3 times 4a3, 12a4. Then you reduce the power of x by 1, you get x like that. Are we together? Meaning if you now differentiate this, you get f triple prime, isn't it? Yes. If you differentiate this, we now have successive differentiation, f triple prime, isn't it? So you differentiate a constant, see 2a2 is now a constant. If you differentiate a constant, you get C0. Meaning this term disappears, isn't it? Then you move, if you differentiate here, you remain with 6a3. Because differentiating x, you get 1. 6a3 is a constant, isn't it? Are we together? You are done with that? Then 12a4 is a constant. If you differentiate x squared, you get 2x, isn't it? Are we together? So 2x times this constant, you have 24? a4x, isn't it? It's just like saying 2 times 12a4, 24a4, then you reduce the power by 1, isn't it? So that is there. If you differentiate for that time. Now when we differentiate this again, meaning we get f4 prime of x, isn't it? Are you seeing that? So what do we have? Differentiate a constant, you get 0. Remember this one is still moving until, isn't it? You get 0. Then if you differentiate this, 24, a4, then plus until where you reach, isn't it? Are we together?
Yes.
Now look at this. If you look at this derivative, now we want at a point, when x is 0. Now we want to see when x is 0, what are these derivatives when x is 0? So can you substitute when x is 0? Start with the first one, the function f of x, meaning where there is x you put 0, isn't it?
Yes.
When x is 0, where there is x you put 0, meaning this one is going to be f of 0, isn't it? See, when this x is 0, meaning all these are going to 0, isn't it? Then what do you remain with? A naught, isn't it? You remain with A, you move to the next one, f prime of 0, meaning when this x, when you put 0, yes, you have f prime of 0. Are you seeing that? Anywhere you see x, you put 0, meaning if you put 0, yes, all this will go to 0. What will you remain with? A1, isn't it? You remain with A,
A1.
you move to the next one, f double prime of 0. Are you seeing that? F double prime of 0, where there is x, you put 0. So you have f double prime of 0. So, meaning all this will go to 0. Anywhere you see x, you put 0. Meaning all this will go to 0. You'll remain with 2a, isn't it? 2a2. Then you move to the next one, f triple prime of 0, where there is x, you put 0. So, this will go to 0. You'll remain with 6a3. Are you seeing that? Then you move to the next one, f dot fourth derivative of 0. When you put 0 here, what do you remain with? There is no x, you just remain with that constant, isn't it? 24? A4. Now, look at this. When you now make a's the subject of the formula, when you make this a's the subject of the formula, it means that a naught is equals to f of 0. When you make a's the subject of the formula, isn't it? Are you seeing that? And this one means a1 is f prime of 0, isn't it? And here a2 is f double prime of 0 over. So you divide both sides of the equation by 2 for you to remain with a2. So it means a2 will be f double prime of 0 over 2, isn't it? Are you seeing that? Then a3. So you divide both sides of the equation by 6. Are you seeing that? What do you get to be a3? F triple prime of 0 over 6, isn't it? Then you move here. What is f4? Divide both sides by 24, isn't it? You get f4 is f fourth derivative of 0 over 24, isn't it? A fourth derivative of 0 over 24. Now look here. Remember, look here. Start with this a naught, a1. What is 24? 24 is the same as 4 factorial. So you can see f fourth derivative of 0 over 4 factorial. Because 24 is 4 factorial, can you press in the calculator? 24 is 4 times 3 times 2 times 1 times 0 factorial. If you expand, isn't it? Because 0 factorial is 1, so it is just like 4 times 3 times 2 times 1 is 24, isn't it? Are you seeing that? Meaning if you have fourth derivative, it is over 4 factorial. Then what is 6? 6 is 3 factorial, isn't it? 6 is 3 factorial. Because 3 factorial is 3 times 2 times 1 times 0 factorial. 0 factorial is 1. 3 times 2 is 6 times 1 times 1 is 6, isn't it? Are you seeing that? So it means if you have f triple prime of 0, then it is over 3 factorial if this here is triple. Meaning if this is f double prime, meaning it is over 2 factorial because 2 is the same as 2 factorial, isn't it? Are you seeing that? Meaning f double prime of 0, if this is double prime, it is over 2 factorial. 2 factorial is the same as 2. Have you seen that? When you have f prime of 0, it means it is over 1 factorial. Are you seeing that? Because 1 factorial is the same as 1. If you have f of 0, meaning it is over 0 factorial, meaning f of 0 is the same as f raised to 0, 0. So when it is 0, it means you have not differentiated it. That's why that 0 is not there. Are you seeing? Are we together? So from here, we now do the substitution. Now see, we know the value of A0, value of A1, value of A2, value of A3, value of A4, isn't it? So once you found the value of A1, A2, A3, A4 in that order, you now go back and substitute them in the polynomial function. Are you seeing that? What was our polynomial function? The polynomial function f of x was given by A0, x0, A0 x raised to power 0, I mean, A1 x raised to power 1, A2 x squared, are you seeing that? Then A3 x3, A4 x to power 4 in that order. Are you seeing the polynomial function? Are we together? So from this polynomial function, can you now start by substituting the values of A, isn't it? The values of A. Is that okay? So you start the values of A. When x is raised to power 0, it is 1, meaning this x raised to power 0 is silent. So you just have A0, isn't it? Are we together? So A0, what is A0? A0 means it is f of 0 over 0 factorial. When it is raised to power 0, it means it has been not differentiated it. Are you seeing? Are we together? Then it is plus, what is A1? Meaning you've differentiated it once over 1 factorial, then x is raised to power that 1. Are you seeing? Then you move, when you have A2, what is A2? It means it is f double prime of 0 over 2 factorial, then x is raised to power that 2. Are you seeing what is happening? Are we together? Then you move to the next one, A3. What is A3? It is f triple prime of 0 over 3 factorial, then we have our x raised to power 3 there. So it means when we have 3 factorial, it is x raised to power 3. Are you seeing that? So you saying you can continue with that same process, meaning if you have f to power 4 of 0, you will have it over 4 factorial, then x raised to power 4. Are you seeing that? You can get the next by seeing the procedure now. Are you seeing that? Are we together? Is that okay? Now this kind of, now we've used the polynomial function of the power series to get what we are referring, this now what we are referring as the Maclaurin's series. So this is the Maclaurin's series expansion of the function f of x at a point when x is equals to 0. So it means the Maclaurin's series is giving you the expansion of the given variable. So if you have function f of x, it is only Maclaurin's series can expand in ascending powers of x. Are you seeing that? Meaning if you want exponential x and you want to expand it in ascending powers of x, then it means only Maclaurin's series can do that. Are you seeing that? Are we together? If you want to expand ln of maybe 3x plus 2 in ascending powers of x, only Maclaurin's series can do that. It is only Maclaurin's series which will give you x raised to power 0, x raised to power 1, x raised to power 2, x raised to power 3, ascending powers of x if the function is f of x. Tuko pamoja? The Taylor series cannot do that. We will see. Is that okay? So this is now the Maclaurin's series. So when we are talking about the Maclaurin's theorem is the Maclaurin's series expansion of a function f of x in ascending powers of x. Are we together? Is that okay? So from the Maclaurin's theorem, this is what we refer to as the Maclaurin's series. So the Maclaurin's theorem, we found that f, when you want to expand a function f of x, you start with f of 0, isn't it? You start with f of 0. Remember 0 factorial is 1, so it just means that's just f of 0, isn't it? Are we together? If you press 0 factorial is, so when you want to expand f of x, you start with f of 0, then plus. If you differentiate it once, it means it is over 1 factorial, then x is raised to power that 1, isn't it? If you differentiate it for the second time, meaning it is over 2 factorial, then x is raised to power that 2. Are you seeing the trend? If you differentiate it for the third time, f triple prime of 0, meaning it is over 3 factorial, then x is raised to power that 3. Are you seeing how to deal with the Maclaurin's series? So the Maclaurin's series is used to expand in ascending powers of x. Only Maclaurin's series can do that. Are we together? Is that okay? Yes. Now, we want to use the Maclaurin series to get the Taylor's series. We want to use the Maclaurin series to get the Taylor series.
Before that,
yeah.
After you put in the same when x is equal to 0, enter f bracket 0. Let's say when x is 7, just
when x is?
Let's say when x is 7.
When x is 7, that is now the Taylor series. It is where we are heading to. Meaning in the Maclaurin series, x must be equals to 0. Is when you get ascending powers of x. When x is equals to something which is not 0, that is now Taylor series. Are you getting it? So x must be equals to 0 is when it is Maclaurin series. So when x is equals to any value which is not 0, then it is the Taylor's series. It is the Taylor series. Are we together? So can we now go to the Taylor series when x is equals to anything which is not 0? Are you seeing that? Are we together? Yes. Good. So move to the Taylor series. So we've seen the Maclaurin series from the Maclaurin's theorem. The Maclaurin's series. So let us go to the Taylor's theorem. So the Taylor's theorem actually is divided into two parts. There's a Taylor's theorem for the expansion of a function f of x, and there's a Taylor's theorem for the expansion of a function of f of x plus h. Are you seeing that? Somebody will give you maybe sine x to expand sine x plus h in Taylor series. Are you seeing that? So sometimes you will be told to expand this just as a function of x or as a function of x plus h. We want to see how that is coming about, isn't it? So when you are told to expand as a function of x, it must be at a certain point, isn't it? It must be at a certain. We want to see how that is coming about. So go to Taylor's theorem. Taylor's theorem. So the first case of the Taylor's theorem, we want to see the Taylor series expansion of a function f of x at a point when x is equals to 0. Are you writing what I'm saying? The Taylor series expansion of a function f of x at a point when x is equals to a. Is that understood? At a point when x is equals to a. So the Taylor series expansion of a function f of x at a point when x is equals to a. Okay? Now, start here. From Maclaurin series, what have we seen? We've seen in Maclaurin series, if you want to expand the function f of x, the point x must be equals to 0, isn't it? Meaning you will start with f of 0, so after f of 0, if you differentiate it for the first time, meaning if it is f prime of 0, it must be over 1 factorial because of 1 prime, isn't it? When it is over 1 factorial, it means x is raised to that power 1, isn't it? Are we together? When you now have f double prime of 0, it means it is over 2 factorial, then x is now raised to power that 2, isn't it? When it is triple prime of 0, it means it is over 3 factorial, then x is raised to power that 3, isn't it? So this is the Maclaurin series. Now we want to use this Maclaurin series to get the Taylor series as a point when x is equals to a, isn't it? At a point when x is equals to a. Now, look at this. Remember when you have x, look at this. We have here f of x is equals to f of 0 plus f prime of 0 over 1 factor. Remember x can as well be written as x minus 0 raised to power 1 because x minus 0 is just x. This is x raised to power 1. You can rewrite it as x minus 0, isn't it? X minus 0 is just x. But we are doing that one because we want to get the Maclaurin series. We want to get the Taylor series from the Maclaurins, from what we have. I'm using what we have to get what we don't have. Are you seeing that? Then the next term here, we have f double prime of 0 over 2 factorial. Then x can as well be x minus 0, then it is squared because x minus 0 is just x. Are you seeing that? Are we together? then plus f triple prime of 0 over 3 factorial, then x is cubed. This x, you can express it is x minus 0. So x minus 0 is just x to the power 1, x to the power 2, x to the power 3. Are you see? This was an expansion at a point when x was equals to 0, isn't it? But now we want to get an expansion at a point when x is equals to? Are you seeing that? At a point when x is equals to? A. So at the point when x is equals to a, what does this imply? It implies this. At a point when x is equals to a, simply implies when you bring a on this side of the equation, what are we going to have? When you bring a on this side of the equation, we are going to have x minus a to be equals to 0. Serio? That is the first point. So when you are expanding at the point when x is equals to a, it means the value you are, when you are expanding this series, you got it at the point when x was equals to 0 is what gave you this series, isn't it? But now when you are expanding at the point when x is equals to a, that simply implies a is equals to, see, that is the implication. Because the implication from this series is x is equals to 0, isn't it? So when you are now saying x is equals to a, then you are simply trying to tell us a is equals to 0. See, that's what we are trying to say. Because you got this series by making x to be equals to 0, isn't it? But now when you are saying x is equals to a, then you are trying to say, if you compare the two, a is equals to? A is equals to 0, isn't it? So that when you have x equal to a, if you bring a this side, you get x minus a to be equals to? Are we together? Is that okay?
Yes.
Yes. So at a point when x is equals to a, at a point when x is equals to a simply implies that a is equals to 0 when you do the comparison of the two ones, because x equals to 0 gave you this, and what it gave you is what we want to use, isn't it? And we want to use it at a point when x is equals to a, like that your case when x now is equals to 7, isn't it? Are you seeing that? So when you compare the two equations, it will simply imply that a is equals to? A is equals to? 0. So what does that mean? Anywhere you see 0 in this equation, you put what? A. You put a. That is what it means. So here we have f of x is equals to f of anywhere you see 0, you put a. That's why we're saying x is equals to a. If you bring a this side, you get x minus a, isn't it? Because somebody will come and tell you to expand this function in ascending powers of x minus 1. Are you seeing that? When they say in ascending powers of x minus 1, and you know x is equals to a is where you are getting this factor x minus a. So if you say x minus a, you compare with x minus 1, then from here you simply see that a is equals to? Are you seeing what they're trying to tell you? Meaning for you to make an expansion at a point in ascending powers of x minus 1, it is another way of them telling you that expand it when a is equals to 1. Are you getting? Is that okay? Good. So that is f of a. Do the substitution here. Plus f prime of a over 1 factor, then x minus a raised to power 1. Meaning anywhere you see 0, you now put a, because now x is equals to a, isn't it? Anywhere you see 0, you put a. You move to the next one. If you have f double prime of a, then it is now over 2 factorial, then x minus a squared. Where there is that, you put a. And you continue with the same process up to where you want to reach, because sometimes they will tell you up to the term in x cube, meaning you reach x cube, isn't it? Sometimes they will tell you up to the term in x to the power 4, meaning you reach x to the power 4. So here we reach up to the term in x squared, isn't it? But here it's not just x up to the term in x minus a squared, meaning you were told if a was 1, then where they say you put 1, so they will tell you in ascending powers of x minus 1 up to the term in x minus 1 cubed, isn't it? Are we together?
Yeah.
So this is now the Taylor series expansion of a function f of x at a point when x is equals to a. Are we together? This is the Taylor's series expansion of a function f of x. A Taylor series expansion of a function f of x at a point when x is equals to a. Are we together? at a point when x is equals to a. So that is how we get that kind of Taylor series, meaning when x is equals to a, you are expanding in ascending powers of x minus a. Have you seen that? Because when x equals to a, if you bring a on this side of the equation, you get x minus a. Have you seen that? So the Maclaurin series is expanding in ascending powers of x alone. Have you seen? But the Taylor is now in ascending powers of x minus a, meaning a may be anything. If a is 7, it is ascending powers of x minus 7, isn't it? If a is negative 2, then it is ascending powers of x plus 2. Because if you bring negative 2 this side of the equation, it becomes positive. Are you seeing that?
Yes.
Because you'll be told maybe to expand at the point when x is equals to negative 2. So you bring negative 2 on this side of the equation. Then you have there, it means you are expanding in ascending powers of x plus 2. Isn't it? Is that okay? Very good. Now, that is now the Taylor series expansion of a function f of x at a point when x is equals to t. Now, the second case, there's now the second case of the Taylor series, according to Taylor's theorem. The second case is the expansion of a function f of x plus h. F of x plus h. So, how do we now expand a function f of x plus h? Now that is now very simple. This is how it goes. Now look at this. We know, look at this. This Taylor series is at a point, we have here x minus a. So if we want ascending powers of h, because you will hear them telling you, expand the function f of x plus h up to the term in h cubed, meaning the ascending powers are now for x, h. Are you seeing that? So how do we expand a function f of x plus h in the Taylor series? Isn't it? Very simple. So it means the powers of h is what is going to ascend. So if you look at this Taylor series, what is ascending? So it is x minus a at the point when x is equals to a, isn't it? So at the point of when x is equals to a, we have x minus a. So if we have x minus a, it is this x minus a, we are now doing what we call the change of variables. Are you seeing that? Meaning where there is x minus a, you put what? H. We are now doing the change of variables. We no longer need ascending powers of x minus a, but we need ascending powers of h. Meaning where there is this x minus a, we put h, so that we have h to power 1, h to power 2, h to power 3. Are you seeing it is now ascending powers of h? Meaning what we are doing in this first case of the fifth theorem, we are just changing the variables, isn't it? We are just changing the variable. So it means this x minus a, you let it to be equals to h. Meaning anywhere you see x minus a, you put what? H. And anywhere you see x, you put what? You make x the subject of the formula. Meaning anywhere you see x, you put, because a going the other side, you get x to be a plus h. So it means anywhere we see this x minus a, we substitute it with h, isn't it? And anywhere we see this x, we put what? Isn't it? So this is f of x. It now becomes what? F of a plus h. Because where there is x, you put the value of x is what? A plus h. Are you seeing that? A plus h to be equals to what? F of a. Remember, there are only two things we are substituting. X minus a, this terms which is h, and our x we are getting rid of, which we found to be a plus h if we make it the subject of the formula, isn't it? This a we are not interested in. It is part of this, isn't it? We are only interested in this h and removing this x. We don't need this x. And this x is the same as a plus h. Okay? Yes. I have continued with the substitution, then it is plus f prime of a over 1 factorial, then h is raised to power 1, isn't it? You see that? X minus a, where you see it, you put h. Meaning if I have f double prime of a, it is over 2 factorial, then h is squared, isn't it? Are we together? Then plus, now if it is to power 3, so you've seen the trend. Over 3 factorial, then h is raised to power 3 in that order, isn't it? Are we together? Are we together? Now if you look at this problem, remember the function you are dealing with in the second case here, you wanted to expand f of x plus h. But this is not x plus h, this is a plus h, isn't it? See, that is change of variables. Meaning, how do I get x plus h from a plus h? Change of variable. I now want f of x plus h. Meaning, anywhere you see a, you put x. Are you seeing? Yeah. Because this is a plus h, but I don't need a plus h, I need x plus h, isn't it? So it means anywhere I see a, I put what? Isn't it? So it means f of x plus h is going to be what? Anywhere you see a, you put x. So f of x plus h is f of x plus f prime of x over 1 factorial, then h is raised to power 1, isn't it? Then it is plus f double prime of x over 2 factorial, then h is squared, isn't it? Yes. Then it is plus f triple prime of x over 3 factorial, then h is cubed in that order, isn't it? So this is now the Taylor series expansion of a function f of x plus h. Are we together? That is the Taylor series expansion of a function f of x plus h. So are you seeing, when we are dealing with power series, we have 3 power series, isn't it? The first one is the Maclaurin series, the second one is the Taylor series expansion of a function f of x, and the third one is the Taylor series expansion of a function of x plus h. Isn't it? Are we together? So, sometimes you will be given a function like this. You will be given a function like this. If somebody gives you a function f of x to be equals to ln of 3x plus 2. So it means this is the function f of x. Meaning you expand it as a function f of x. When you are told in Taylor series, you will be told at that point, isn't it? Meaning this is what you use if you are told it is Taylor series. But if you are told it is a function f of x plus h to be this, meaning you use this. Those are 2 different things. But you see, the value is the same, but the function in defining them are different. Are you getting the point? You have to know the function you are dealing with. Is it a function f of x or is it a function f of x plus h? Which one are you told to deal with, isn't it? It is only Maclaurin series when a is equals to 0. So can we now devise a means of mastering this series? There's a very simple means of mastering this series. You don't need to master the Maclaurin series. You only need to master the Taylor series. Are we together? The Taylor series you can master like this. You can say, when you start with the function f of x plus h to go to f of x to go to f of a. This is a means of mastering this series. Are we together? You say f of x plus h to be equal to f of x to be equal to f of a. So if you want to expand f of x plus h, meaning you take this side. Meaning anytime you are expanding a function f of x plus h, you start from f of x. That is just an algorithm of mastering a concept. Are you seeing that? Anytime you want to expand f of x plus h, you start from f of x. Meaning this one, I'm going to start from f of x. Are you seeing? Then plus, then you go to f prime of x, you leave a space where you're going to write something. Then plus f double prime of x in that order, then you start. When you have f of x, that means it's 0 factorial over x raised to power 0. Those are silent, you don't need, isn't it? If I have f prime of x, then it means it is over 1 factorial, and over 1 factorial, and because this one has h, it means h raised to power. When I have f double prime of x, meaning it is over 2 factorial, then h is. Are you seeing how to get there? Are we together?
Yeah.
Meaning if you now want to expand this part, if you want to expand the function f of x, meaning you take this side. Meaning when you are expanding a function f of x, you start from f of a. Are you seeing? Are we together?
Yes.
So if I want to expand a function f of x, I start from f of a. After f of a, I go to f prime of. Then you leave a space where you are going to write something, isn't it? Then after f prime of a, I go to f double prime of a in that order, isn't it? Then you know this is 0 factorial, everything is silent here, isn't it? So when it is f prime, it means it is over 1 factorial, isn't it? And when I'm dealing with f of a, that is ascending powers of x minus a, isn't it? Meaning here I have x minus a raised to power 1. Now you see the concept? Because when it is when you are starting at f of a, you know you will have x minus a because it was at point x is equal to a. When a comes this side, meaning the powers which is ascending is x minus a. If here you have f double prime, meaning it is over 2 factorial, then your x minus a is raised to power 2. If you get the third one, which was that, meaning it is over 3 factorial, then your x minus a is raised to power. Are you seeing how getting this series are very simple? Are we together? Then from there is now where you now see the Maclaurin series. The Maclaurin series is at a point when a is equals to. The Maclaurin series is at a point when a is equal to 0, isn't it? Meaning if you put 0 anywhere you see a, you will get the Maclaurin series. So can you put 0 anywhere you see a, you will get the expansion of f of x is f of 0 plus f prime of 0 over 1 factorial, then x raised to power 1 because x minus 0 is just x. Are we together? Then plus f double prime of 0 over 2 factorial, then x squared, because x minus 0 is just x. So you see, you start from x plus x, then f of x, then f of x for the Maclaurin. Then you have the 3 series. Is the concept understood? Is the concept understood? Yes. Power series will never miss in your area. It is always there.